So just a reminder that probability is a number that represents the likelihood of an event happening. And you can write a probability as a fraction. That's usually how we start probability problems. Or you can write it as a decimal. Or you can write it as a percent. And the problem should specify which format we want you to write the probability in. When you're writing probability, again, you're going to start with creating the fraction. And this is kind of your formula for the fraction. On the bottom of your fraction, you're going to put the total number of possible outcomes. And then the top is the total number of favorable outcomes, or the outcomes that you care about. Now, what we're going to do today is we are going to find probabilities of unions and intersections. So just a reminder that when you see A intersect B, it means A and B. And then when you see A union B, it means A or B or both. So finding probabilities with unions and intersections gets a little more complicated, but it's not too bad. Here's a formula you can use to help you find those probabilities. You can also just use the table, and I'm going to show you how to just use the table because I think it's a little bit easier. So let's go ahead and take a look at this example down here. So let's say in the math club we have 34 students. As we go through, let's go ahead and fill this in. So we have 34 students. That's the total number of people in the math club. 11 of the students are seniors. So in the senior column, I'm going to total it to 11, including 7 of the 20 girls. So 7 of the seniors are girls, and there's a total of 20 girls. A student is chosen at random from the club. We want to fill in the table, which we've already started, and then find the following probabilities. And you'll notice here it tells you express your answers as simplified fractions. So we're going to focus on fractions for this one. Let's go ahead and finish filling in our table. We know that the senior column has to total to 11, which means there's 4 boys. The girl row has to total to 20, so there's 13 non-seniors. The total row at the bottom has to total to 34, which means there's 23 non-seniors. So there's 10 non-senior boys and 14 total boys. So my first question is finding the probability of choosing a boy. So I'm going to start by making my fraction. The bottom is the total number of possible outcomes, so 34. And on the top, I'm going to put the total number of boys, which is 14. So 14 over 34, I'm going to try to simplify that fraction. I can divide the top and the bottom by 2, and I get 7 over 17. Next, let's find the probability of choosing a senior. So again, I'm choosing out of 34, and the total number of seniors I have is 11. So that is going to be my probability, 11 over 34. Okay, the next one I want to do the probability of boy intersect senior. So that intersection sign means boy and senior. So I've got to find the numbers over here that represent the boy seniors, and there's 4 of them. So my fraction is going to be 4 out of the total 34, which simplifies to 2 over 17. Okay, I'm going to go ahead and erase my little highlighter so I can use it for the next one. So intersections, one we just barely did, not too bad. Unions in the next one are going to be a little more complicated. So what the probability of choosing a girl, union, non-senior. Remember that union means or. So that means that I need to count all the girls, so anyone who's a girl, or a non-senior. So I also need to count all the non-seniors. So you want to make sure you catch everyone who's in either of the groups or potentially in the overlap of the 2 groups. So I'm going to go ahead and add all those up. I have 7 plus 13 plus 10. That gives me 30 total. So there are 30 people in the group I care about out of the total 34 in the table. I simplify that fraction. I get 15 over 17. Okay, so that is the probability of choosing a girl or non-senior or both. Okay, so let's go ahead and talk about a new type of probability. We're going to talk about what's called conditional probability. And we have heard the word conditional before. We talked about it when we were talking about marginal and conditional distributions. And if you'll remember, marginal meant that we were dealing with just the totals, and conditional meant we were dealing with a subgroup. So conditional probabilities get a little bit more interesting because instead of looking at the total number of people, you're just looking at a subgroup. And the symbol that you're going to see with conditional probability is this vertical line, and it means given. So for example, this kind of probability statement here reads, the probability of choosing someone who has lung cancer given that they smoke, which means that I'm not looking at everyone in the population, I'm just looking at the smokers, and I'm figuring out what percent of them have lung cancer. Okay, we've got a conditional probability formula right here, which can be helpful as well. Let's go ahead and get into a specific example of this, though. Let's say we've got an ice cream shop that keeps track of whether people order vanilla or chocolate ice cream, and then whether they ordered a sugar cone or a waffle cone. We've got all the data on the inside of the table. We want to start by just filling in all of our totals really fast. The total in the vanilla row is going to be 61. Total in chocolate is going to be 98. Total overall is going to be 159. Sugar cone total is 86. Waffle cone total is 73. Okay, we've got our totals filled in. One more thing to notice before we move on is we want to express our answers as fractions. Notice it doesn't say simplified fractions. So we're just going to write a fraction and then be done. We don't have to worry about simplifying. Okay, so first I want to know the probability of choosing vanilla given that I chose sugar. So vanilla given sugar. So the given means that I only care about people that are in the sugar group. So when I start looking at my fraction, I'm no longer looking at everyone. I am just looking at the people that are in the sugar cone group. So there's a total of 86 people in the sugar cone group. And of those 86, 35 chose vanilla ice cream. Okay, let's do the next one. We want to find the probability of choosing of sugar given vanilla. So this is sugar given vanilla, which means that I'm only looking at people that fall in the vanilla group. So the total in the vanilla group is 61. And of that 61, 35 chose a sugar cone. Okay. The next one is the probability of choosing chocolate given that you chose sugar. So I'm looking at just the sugar cone group again. So the total is going to be 86. And of the 86, 51 chose chocolate. So 51 of 86. Okay, hopefully you're starting to get the hang of this. So if you want to just go ahead and start filling in the next ones, that's totally fine. So sugar given chocolate. So I'm just looking at the chocolate group. So let's see. In my chocolate group, I have 98. So that goes on the bottom. Of those 98, how many of them chose sugar cones? 51. Now notice this 51 on top, it's not the total number of everyone who chose sugar cones. It's just the sugar cones that are in the chocolate group. So we're just looking at a subgroup, which is really important for conditional probability. Okay, let's go ahead and look at some other examples then. The next, we have a bunch more probabilities we're going to calculate. And here we're not going to interpret them in words. We're just going to calculate the probabilities as fractions. So the first one is the probability of chocolate given that you chose a waffle cone. So total waffle cones goes on the bottom, and then chocolate waffle cones goes on top. Probability of vanilla given waffle. So total waffles go on the bottom, and then the vanilla waffles go on top. Okay. Probability of waffle given vanilla. So again, vanilla is going to go on the bottom. And on the top, I'm going to put the waffle cones that are in the vanilla group. And then the probability of waffle given chocolate. So I'm going to start with the total chocolates on the bottom, and then the 47 chocolate waffles on the top. Okay. So with these, it's really just making sure we pull the right numbers. Now you'll notice after I get through those 4 examples, I just get back to these normal probabilities that I know how to handle. These are not conditional probabilities. There's none of that vertical bar stuff that tells me it's conditional. So now I'm back to looking out of the total group. So in example E, I just want, the probability of choosing vanilla. I don't care what kind of cone you chose. I just want to know what % chooses vanilla. So we know that 61 of the 159 choose vanilla. So with waffle cones, it's going to be 73 of the 159 chose waffle cones. For sugar cones, I'm going to look at the total sugar cones over the total number of everyone. And then for chocolate, I'm going to look at the total chocolate over the total of everyone. So notice the one thing in common with all of these, they all have the same denominator. And that's going to be the case. The denominator will always be the total unless you're dealing with a conditional probability statement. Okay. All right, now we're going to do a bunch of probabilities of intersections and unions. So for all of these, since they're not conditional, we know the denominator for all of these is going to be 159. So I'm just going to go ahead and put that in for all 8 of these. I'm not dealing with conditional probability, so I am dealing with the entire group of people, the entire data set. Now, these intersection ones, the first row, are going to be pretty easy. I just want the people that are in the vanilla and sugar group. So vanilla and sugar is just this 35 right here. So 35 goes on top. Okay. Okay, the next one is vanilla and waffle. So how many chose vanilla and waffle? That was 26 of the 159. Chocolate and sugar is 51 over 159. And chocolate and waffle is 47 over 159. So our intersections, super easy. Okay. The next row is all of our unions. These ones get a little more complicated. So I want to count everyone in the vanilla group as well as everyone in the sugar group. So if it were me, I would recommend just using like the inside values and not using your totals. Using your totals, there's a way to do it, but it can lead you to some mistakes. So I'm just going to use the inside numbers in my table. I want to count the entire vanilla row, so the 35 and the 26, and additionally everyone in the sugar row. So I've got to count the 35, 26, and 51. So I'm going to go ahead and add all those up. I get 112, so that's what goes on top of my fraction. Okay. Next, I'm finding vanilla or waffle. So I'm going to highlight all the vanillas, all the waffles, and then add them up. I get 108. Whoops, didn't mean to erase that whole column. Next, I want chocolates or sugar. So I'm going to count up all the chocolates. So 51 plus 47, and then plus my sugar cone, so plus 35. I get 133. And last, I want my chocolate waffle people. So that's going to be 51 plus 47. That catches all the chocolates, plus 26, which catches the last of the waffle cones. And I get 124 on top. Okay. Now notice that all of these are in fractions. They're not simplified. This would be a good data set to convert everything into percents so that we can maybe more accurately see and more easily see what's actually happening at this ice cream shop. Okay. Let's go ahead and take a look at another example here. So new data set. Now we're dealing with a group of 100 people that were sorted into males and females, and then whether they have an after-school job or they do not have a job. Okay. So the first one is the probability of having a job given that you're male. So I'm just looking at the males. So on the bottom, I'm going to put the total number of males. And then of those males, how many have a job? Well, 21 of those males have a job. Okay, so I've got my fraction written. That's always my first step. And I want to look back at my instructions. It says express all probabilities as decimals rounded to the nearest thousandth. Remember, thousandth means 3 decimals. So I'm going to grab my calculator, 21 over 48, and I get 0.4375, which is going to round to 0.438. Okay. All right, next one. What's the probability of being female given that you have a job? So now my total is going to be everyone with a job, so 54. Then of those 54, how many of them are female? 33. So 33 over 54, it's going to give me 0.611111 forever. So it's going to be 0.611. Okay. Next one is probability of being male given that you do not have a job. So this second phrase, that's going to be the denominator of my fraction. So the no jobs total to 46. And then of those no jobs, 27 of them are male. So I'm going to do 27 over 46, 0.587. Be careful with your rounding. Remember that on your test, it's going to be on Canvas. You have to make sure you're rounding correctly. Okay, probability of no job given that you are female. So again, I'm looking at just the females. So 52 on the bottom. Of those 52, 19 do not have jobs. So I'm looking at 19 divided by 52, which gives me the probability 0.365. Okay, these are all interesting and great probabilities. Let's answer some questions in here. A student from the sample works at McTaco. What is the probability that the student is male? So what we know about the student that we're dealing with is that they have a job. So we're not looking at all the students, we're just looking at the students that have jobs. So I'm going to start by putting the total students with jobs at the bottom, so 54. And on the top, I want to look at what percent of those or how many of those are male. So of the after-school jobs, 21 of them are male. So 21 over 54 is going to be 0.389. And that's the probability of finding if the student that works at McTaco is male. Then the next one I want to look at is a student from the sample more likely to have a job if he is male? So I want to calculate two different conditional probabilities. I want to know the probability that he is male. Well, not that he's male. We want to have the probability that he has a job given that he's male. And then I want to calculate the probability that he does not have a job given that he's male. Okay, so I just want to know, if I'm just looking at the males, is it more likely to have a job or not have a job? So again, I'm only looking at the males, so my denominators for both of these are going to be 48. Okay. And we can see that 21 of the 48 males have jobs, and 27 do not. If I want to convert this to a probability, it's going to be 0.438 have a job, and then 0.563 do not have a job. So they are more likely to have no job. Okay, so this is one of those questions that we can answer using conditional probabilities. The other question we can answer about using conditional probabilities is whether two events are independent or not. Okay, I gotta erase this. I forgot I started working through this already. So two events are considered to be independent if an event occurring doesn't affect the probability that the next event will occur. So for example, some examples of independent events would be like rolling a dice and then flipping a coin, because the dice doesn't affect the coin. Or waking up early and wearing jeans to school, because the time you wake up doesn't really affect if you wear jeans. Or winning the lottery and having blue eyes, because your eye color doesn't affect whether you win the lottery or not. So independent means they are completely independent from each other. Dependent events means that doing one affects the other. So for example, speeding is going to affect your likelihood of getting a ticket. Or doing your homework is going to affect the likelihood of you getting an A. I can attest to this. You do your homework, you're more likely to get an A. Or being tall and playing basketball. right? That's going to, if you're tall, you might be slightly more likely to play basketball. So those are dependent events. So most events in the real world are dependent. They depend on each other. A lot of a lot of our game type things, rolling dice, spinning spinners, flipping coins, those are going to be independent. And what we want to know is we want to be able to look at a table, a real data set, and decide if the event of A is independent from B. And to do that, we're going to use this formula. If the probability of A is equal to probability of A given B, then A is independent from B. So to check independence, you've got to check the probability of A given B. They have to be exactly the same. If they are, we say yes, they're independent. If they're not, we say no, they're not independent. So let's look at some data and decide if things are independent from each other. So we've got the number of students in a high school is 1,400. So let's fill that into our table. We have a total of 1,400 students. Each student has to take a math class, either algebra or geometry, and they have to take language, either French or Spanish. So 550 take French, so the total French is 550. 700 take algebra, so the algebra total is 700. And then 400 take both French and algebra. So there's 400 in this French and algebra overlap. What we're going to do is we're going to finish filling in the table, and then we're going to answer some questions about independence. I'm going to go ahead and just fill in these tables and these values really fast. It's pretty amazing how little information you need to be able to fill in the entire table. Okay, so I've got all my totals, I've got all my subtotals, and we're ready to go. So I want to know is French independent from taking algebra? So I need to calculate two probabilities. The probability of taking French and the probability of taking French given that you take algebra. If those two probabilities are equal, then we've got an independent event. So the probability of French would be 550 over 1,400. I'm looking at the total number. I'm going to go ahead and write these as percents this time. So it's going to be 39.3%. Then the probability of French given algebra means I'm just looking at the 700 algebra kids. How many of them are in French? 400. I'm going to change that into a percent, and I get 57.1%. So the overall question, is French independent from algebra? The answer is no, because those two probabilities were not equal to each other. Let's try it again. Is algebra independent from taking Spanish? So now I'm going to find the probability of algebra and the probability of algebra given that you're already in Spanish. So the probability of algebra is 700 of the 1,400, which I know to be 50%. And then the probability of algebra given that you're in Spanish means I'm just looking at the Spanish-speaking kids. So that's 850 on the bottom, and of those 850, 300 are in algebra. I'm going to calculate that as a percent. I get 35.3%. Those two probabilities are different from each other, so the answer is no. Taking algebra is not independent from taking Spanish. It is dependent on taking Spanish. All right, last one. Is taking Spanish independent from taking algebra? So probability of Spanish given that you're already in algebra. So probability of Spanish, I want to know just how many kids are taking Spanish. It's 850 out of the 1,400, which, if I stick with my percents, is 60.7%. Then I want probability of Spanish given that you are in algebra. So now I'm just looking at the 700 algebra kids, and 300 of them are also in Spanish. When I calculate that percent, I get 42.9%. So the question is, are they independent from each other? No, because the probabilities are not equal. So this is maybe a bad example because we didn't see any examples where they are independent. But just know you're going to follow the same process. If these two probabilities are ever equal, they are independent.